said, a bit about me. So I'm currently a professor at Madison. I do a lot of research on kind of thinking about how to verify probabilistic programs. That's kind of my favorite thing to think about. And I'm soon going to be moving to Cornell University in the fall. Kind of a personal note, it's really nice to be back here again because I think I remember going to OPLSS when I was a graduate student. I think when it was probably like 2013 or something. So it's really nice to be back here and on the other side of things, so to speak. All right, so with that being said, let's get started. So this is kind of the rough menu for things that I was thinking of covering in the next 4 lectures. Today is day 1. I want to think about kind of introducing probabilistic programs. So today will be mostly kind of motivations, maybe key questions and some background. And unfortunately, some mathematical preliminaries, which you might find to be a bit dry. The next 2 lectures, I want to talk about kind of first order probabilistic programs. So you can think about like imperative programs with the random sampling command. I kind of want to talk about 2 methods we have out of many methods to kind of prove interesting properties about these programs. And the final day, I want to briefly talk about kind of higher order probabilistic programs. So these are like functional programming languages that have random sampling and other probabilistic features. This is a really kind of big area. There's a lot of stuff to cover, so I can only really give it a little bit, a little touch on a few things. I've kind of planned the first 3 lectures a bit more carefully. The 4th lecture, I've only kind of sort of sketched. So it's totally fine if things take longer than I expect. I think when I was preparing these slides, I started to think that I was maybe trying to do a bit too much in 4 lectures. So if we cover kind of less material than all of this, it's totally fine with me. Kind of with that being said, I want to encourage all of you to please ask questions. For those of you who are kind of with us watching live, I think this is a good thing, a good reason to watch live. I'll check the kind of the Slack channel. There's a channel called Probabilistic for offline questions. Probably won't monitor that during these lectures. Zoom chat is probably the best way to ask questions during the lecture. Like I said before, I am not set on getting through everything I outlined in the previous menu. So we have to skip over, a lot of topics anyways. So if we go a bit slower and cover some stuff in more detail, I think that's great. And you're welcome to also kind of send requests. If you're curious about something that's not on the menu, you can let me know. If I know anything about it and I think it's interesting, maybe we can kind of put it on. Otherwise, I can point you towards maybe more stuff to read. Okay. Cool. Any questions before I begin? Anything? Okay. Take it as a no.
Okay, here's the question, which is not exact. Do you have other video recordings of these lectures or similar lectures in the same field, same area?
Unfortunately, I do not have other video lectures of this in the same area. So this will be actually the first time. So I've been doing research in this area for quite some time. This is my main research area. But this is actually the first time I'll be teaching a course on this material for various reasons. So unfortunately, I don't have anything else. So anything can happen in these lectures.
Okay.
Okay. Cool. All right. So I just want to start a little bit about some giving an idea of probabilistic programs. What they might be useful for, and trying to outline some of the first kind of divisions between different kinds of probabilistic programs and probabilistic programming languages. Okay. So in my mind, I think there are kind of 2 major applications of probabilistic programs. So the first one is what I've kind of lumped under kind of executable code. So these are kind of programs that are more similar to deterministic programs, in that you write a program in some programming language and you expect to be able to execute this program on like a typical computer, let's say. Of course, there's a lot of details in how you actually implement these things and how you can actually implement random sampling. There's many details here that are important, but broadly speaking, you expect kind of the execution of the program to be described in a straightforward way by what you write down in the language. So I think one common example that hopefully is familiar to many people, but perhaps not all of us, is the example of randomized algorithms, right? So Algorithms are programs. You can write down a sorting algorithm, a search algorithm, and there are many algorithms that are randomized. So one natural question is, why should we study these randomized algorithms? Why is deterministic algorithms not enough? This randomness seems to introduce more variation. Why would we want to kind of do this to our, very carefully crafted algorithm? So computer scientists and theorists have developed many of these randomized algorithms, and there's a few reasons why they consider these things to be interesting. So one common application is that we might be able to achieve better performance compared to a deterministic algorithm by kind of sacrificing a bit of correctness in exchange for better performance, right? So I can give you a guarantee that says maybe, this algorithm is going to succeed like 99% of the time. And in exchange, maybe I'm able to run the algorithm faster or use less space or do something more efficiently, right? So I'm kind of weakening the correctness guarantee, but I can make up for it with better performance. So one of the, basic examples, if you've never heard this before, it's totally fine. But one of the basic examples is called Freiwald's randomized algorithm. And this is a randomized algorithm to check if the product of two matrices is a third matrix. So kind of as input to your program, you're given three matrices, like square matrices, let's say, A, B, and C. If I tell you that A times B is equal to C, and if you want to check this to be, make sure I'm not actually trying to trick you, if you multiply out the matrices, it'll take you something like n to the 2.37 operations. This is the current matrix multiplication.
Is that an exact equality you're looking for, or is it like within a tolerance, machine tolerance?
Let's say exact equality for now. So everything, okay. Yeah, exact equality.
Sure. Interesting.
Right. So for the purpose of much of these lectures, I'm going to be ignoring things like machine precision and finite precision stuff. These are all also very important, but will be at a little bit higher level of abstraction because things are already quite complicated there. Now, Freiwald's randomized algorithm gives you a way to kind of check this A times B equals to C, and with high probability if you make only kind of n squared operations. So you can kind of do this check a little bit faster. There's some small chance that you will fail, which means that you might say that yes, this is correct, even though there's actually A times B is not equal to C. But the hope is that you can repeat this algorithm multiple times if you want to kind of lower your chance of making error. So this is one kind of common mode of using randomized algorithms to trade performance for a little bit of loss of correctness. Okay, another common use, major kind of prototype for these algorithms is to improve performance against worst case inputs. So quite often it might happen that you have your algorithm and usually it performs pretty well against most normal inputs, but on certain kind of pathological or unlikely inputs, maybe your performance of your algorithm is really poor. So for instance, quicksort is one example. Most of the time we expect quicksort to be kind of n log n operations. But if your input is kind of worst case, like for instance, if it's reverse sorted, depending on how you implement this algorithm, you might need to make n squared comparisons. So, a common use of randomization is to kind of smooth out this behavior. So for instance, using randomized quicksort, it's known that you can make kind of n log n comparisons on average, no matter what the input is. So the idea is that even if the input is very worst case, it's really pathological because you're making kind of random choices in the algorithm. It doesn't matter so much, right? That somehow you can't find an input that is worst case against all possible realizations of how you pick the random choices in your algorithm. So somehow you're kind of protected against these bad examples. This is a second very common use. There's other benefits I'm not going to really get into here. For instance, algorithms can be simpler to describe. You may be more concise. In certain cases, they're provably more efficient than deterministic algorithms, maybe using less communication or maybe using less space. Okay, so randomized algorithms, is a class of things where probabilistic programs come into play. Also, yes.
Have a minute. Ashish Kumar asks, is the Freiwald's algorithm for matrices a check, or can it also compute A times B without being given C? So is it
Right. So Freiwald's algorithm is just a check. So this is just for checking. The fastest algorithm for computing matrix multiplication is that n to the 2.37 something, which is constantly being slightly improved. But this Freiwald's algorithm is just for checking. Okay. Cool.
And Akhil Indurti asks, is Monte Carlo or Las Vegas algorithms considered part of these three classifications, or is there something different there?
Right. Right. So I would also consider Monte Carlo or Las Vegas algorithms. For those of you that know, these are algorithms that maybe don't have a finite time of stopping. Like their kind of termination time is not guaranteed to be finite, but maybe their average termination time is guaranteed to be finite. So I'd also consider this to be in this umbrella. Maybe not neatly fitting into any of these categories, but perhaps maybe exchanging performance in exchange for failure.
Thanks.
So I'm kind of just touching on kind of this broad area here. I don't want to go too much into randomized algorithms here. Just trying to motivate the things. Okay. Other questions?
I don't see any right now.
Okay, cool. So another kind of example of how these things are used are in security and privacy. So I'll kind of maybe go a bit faster here. Cryptography is quite well known for using randomization, where you want to use randomness to kind of generate secrets that the adversary doesn't know. So the adversary doesn't know the encryption-decryption key. If they knew these keys, then the security guarantee kind of would be violated. But because we draw kind of maybe encryption or decryption keys randomly, the adversary cannot quite guess what is the secret part of this protocol. Recent work in data privacy also kind of uses random noise to kind of blur private data. The main example that has received a lot of attention is the field of differential privacy, which was proposed maybe about 15 years ago. Again, trying to inject random noise to make it harder for maybe an adversary to figure out what the private data is. Okay. All right, so let me quickly outline one more, which is maybe more PL related. It's for randomized testing. Of course, it's another kind of algorithm or kind of probabilistic program where we're trying to actually execute the code, right? So let's say consider a simple setting where you're trying to generate inputs to a program randomly. And the idea is that you have a huge space of potential inputs to your program, and you can't possibly check every single possible input, right? There's just too many. So by kind of using randomization, you can kind of maybe make testing more effective by kind of avoiding human biases, right? So kind of a human programmer might write certain test cases that kind of maybe are normal or kind of represent expected ways the program might have trouble, but they might have some biases in how they think about the program, whereas a randomized testing or like a fuzzing strategy might not have such biases, right? Because it doesn't know how your program works necessarily. This is a very common and effective strategy for testing programs, for property-based testing like quick check, or fuzz testing like AFL or Google's like OSS fuzz. There's many projects built on kind of randomized testing. Okay, so kind of stepping back a bit, I started by saying there were kind of two broad classes or applications of randomized or probabilistic programs in my mind. So the first one is kind of these executable code where you're trying to run the program. The second kind of probabilistic program is what I think of as a modeling tool, or like kind of like a modeling aid. So generally here, the application is a little more interesting or a little more subtle, where you're not necessarily interested in running the program. Yeah, you might be or you might not be. Okay, so here you're kind of using randomness to represent uncertainty. You're trying to model some kind of uncertain situation in the real world, perhaps, and certain bits of information you don't quite know about, right? So you kind of just assume that, like, let's suppose that this unknown quantity here is modeled by a random variable. Okay, it's uniform somehow or something. And then you want to kind of try to answer questions about the model you've constructed. Okay, again, this might involve running the program, or it might not involve running the program. Okay, so there are many kind of uncertain things you might want to model in real world situations. One example is kind of failures. So you try to model like a computer network, and certain links might fail or not. It's hard to say, as someone modeling the situation, when you think a link is going to fail. Because who knows, there's many reasons a link might fail. So you might say, well, I know that the link fails with a very small probability, maybe like, 1 in 1,000 it's going to fail. So I'm going to pretend that this link is going to fail, drawn from some random distribution that, it fails with probability 1 in 1,000. And I'm going to kind of simplify all the real world complexity that makes this link fail. I'm just going to pretend that there's some random process that makes it fail on average 1 every 1,000 hops or whatever. Another example is maybe like tomorrow's temperature. Again, meteorology is really complicated. I can't kind of pinpoint tomorrow's temperature exactly, But I might be able to say, given past data and my model about how the weather works, which might be very complicated, I can give you some distribution of what I believe tomorrow's temperature is going to be, right? So it's not like a point, like exactly 75.2 degrees, but there's some distribution and I have some uncertainty about exactly what the temperature is going to be. Okay.
Tomorrow's stock prices?
Sure. Stock price is another example, like tomorrow's winning lottery numbers, any kind of random or uncertain process, you could in principle model as some kind of probabilistic process. Okay. Whether or not the model corresponds to reality is another question. Hopefully it does, but it might not. And there's many philosophical questions about what exactly it means for this to be randomized, but I'm trying to steer clear of those questions for this talk. But like I said, the main motivation is kind of different from the first class, where you want to actually run the program. Right? So, I want to model some real-world data generation process. Whether a link fails, tomorrow's temperature, stock price, whatever. And it's maybe less important is generating data from this distribution. Like I might, if I have a way to model tomorrow's temperature, I might not really care about generating many candidate temperatures for tomorrow. I just want to kind of see if it matches with the existing data or not. But somehow generating data, might be important, but it's not the primary concern. Okay. So, some examples of this kind of program are kind of like for machine learning is kind of based on this paradigm. Where kind of humans largely design a model of how data is generated. And this model has unknown parameters that we do not know. And then based on data collected from the real world, we would like to infer parameters of the model. Right? So given a lot of temperature data from the last year, maybe I want to infer some relation between temperature and, I don't know, wind speed or something like this. So another kind of more concrete example is kind of learning the bias of a coin. So maybe here, suppose I've given you this coin that I'm telling you it might be biased, it might be fair, you don't really know. And you're given a bunch of data that's generated from flipping this coin many, many times, right? So you have Boolean data, like a string of Booleans, and unknown parameters may be the bias of the coin. So you don't know this thing. So you can flip the coin many times, and then you try to infer or guess what do you think the bias of the coin is, right? So if the coin is always giving you tails, then you're like, well, it's probably going to be a very biased coin. If the coin is usually giving you heads and tails with roughly equal proportion, you might infer that, well, probably the bias is somewhere around 50%, as close to being a fair coin. Okay. So this is kind of like machine learning applications, but this kind of modeling perspective is not really limited to just machine learning. Another example that I like to use is in the field of approximate computing. The idea is that you're kind of computing on unreliable hardware, right? So idea is that hardware operations may occasionally give the wrong answer. So if you kind of do a bunch of additions, maybe once in a long time, like 1 in every million additions, maybe it gives you the wrong answer. So there's many reasons for studying this kind of approximate computing, but one motivation is that in some cases you can get lower power usage if we allow more errors. Right? So you can save a lot more on power by, again, having some small chance of the hardware giving you incorrect results. Okay. So here again, it's not really like the failure is really like drawing a source of randomness, like flipping a coin and deciding whether to fail or not. It's more like because of the chaos of physics or whatever. Every once in a while you will get a failure. Okay. And this is something that you can also model as a probabilistic program, where you kind of model failures as drawn from some distribution. You can, if you might not know this distribution, you can run the hardware many times and estimate the failure rates. You'll estimate that every 1 in a million operations you have the wrong answer. And then you can write a randomized program that describes kind of an approximate program, or like a program running on approximate hardware. It's every time you do an addition, you say like there's a small chance of it failing and giving me some arbitrary results or something like this. Okay. So this is kind of the second kind of broad kind of application of probabilistic programs that I see. So it's a little bit different from the first kind. Okay. Any questions before I go on?
So for this this notion of approximate computing to work, do you need to have built a underlying probabilistic model of the hardware itself, and how does that interact with these different layers? Let's say if you have a probabilistic program running on approximate hardware.
Right. So from the modeling perspective, like the better your model, I guess, that the more realistic your predictions that you can make. I think you could give a very rough model and say, I'm just going to say that my errors are drawn kind of like independently from some distribution. So each operation has an independent chance of kind of failing with probability 1 in a million or something. This is one way of modeling the errors. But if you study the hardware more, you might think, well, actually, this is not really a realistic model because maybe errors are correlated, right? So maybe because of how the hardware works, once this operation fails, then that other operation is also guaranteed to fail. So I can't really model them as independent draws because that's not realistic, right? So I think the modeling perspective is that you're trying to match some real world data, right? So the data is generated by some process that, frankly, we don't understand very well. You can give better and better models to model what's going on. And these will get more and more complicated, presumably. But you have many reasons also for not giving the most complicated model possible, right? So even a simple model might give you some insights, about, for instance, if I run this program, like, what is the chance I expect to get the wrong answer? This is one kind of typical question you might worry or kind of wonder about your approximate program. So like, what is an upper bound on the error I get, right? So what is the chance that I just get something completely bogus? And I can try to answer this with, more and more precise models.
Makes sense, thanks.
Yep.
I have a question. It's related to, like, could you clarify the difference between executing code and modeling? Because I'm coming from the electrical engineering side, and normally we use like a tool like MATLAB, and you're programming probability distributions, and generally what we are programming, we call that as the model. So I was wondering whether there's a difference in the way you're interpreting the word model.
Right. So yeah, these are not really formal terms. These are kind of terms that I've kind of invented on my own, or kind of just made here. I think the difference for me is that the first class of programs, you're intending to run them. Like, that's the intended application. Like, you write a cryptographic protocol, you're intending to execute it. You're intending someone's going to execute it. Maybe not you, but someone else is going to run the program, and that's the main way you might use the program. For something like modeling, in the way I'm using it, you might want to run the program, but you might not, right? So for instance, in this approximate computing program, the model, as I've described it, is not actually the approximate program, right? It's not actually running the approximate program. It's saying, each operation might fail with some chance. I'm going to pretend it's going to be randomized like this. So given this kind of program, I might not be interested in actually running it, right? Instead, I might be interested in answering questions about the distribution it's describing. So I might want to know, what is the chance that this thing will fail, right? So this is not obtained by kind of running a probabilistic program, once or many times, though you can maybe estimate it. Like, I might want to answer this question, answer something about the distribution itself rather than produce a sample, if that makes some sense.
Oh, so is it similar to like using a tool like Mathematica to solve an equation and getting a solution for an equation, and the other case wherein you're using MATLAB for solving a linear algebra equation?
Yes, it could be something like that. I think.
I think it's like symbolic. Is it difference between a symbolic solving of an algebraic equation and in which you get the final answer out, but you're not.
Right. I think the difference I'm saying is not necessarily symbolic. So you might actually also want something numeric, but it's more, you're trying to answer something about the distribution itself rather than producing a sample. I think that is the fundamental difference.
Okay.
But symbolic versus numeric, I think both of them have their place.
Okay, thank you.
Yeah. All right. So, okay, this is just still motivating. I want to now give since this is OPLSS, the focus of this lecture will definitely be on the programming languages side of things. I want to give a quick overview of what I see as the main questions and research directions in probabilistic programs. So, what do you want to know about probabilistic programs and probabilistic programming languages? In my mind, I think there are four especially important areas, or that most important for programming languages. These four are semantics, verification, automation, implementation. Okay, so semantics, if you've been following some of the other lectures, you may have gotten a good idea about this already. But I just mean this is kind of describing what do programs mean mathematically. So, we want to semantics kind of specifies what a program is supposed to do. These programs that you're writing in these languages, they might generate very complicated distributions, and the desired or intended behavior of the program may not be obvious. Like, what is the answer supposed to be, even ignoring any implementation concerns, right? Like, what is this program supposed to compute? Like, what does that instruction mean mathematically or otherwise? So some common tools are kind of maybe demutation semantics, like defining program behavior using mathematical concepts, or operational semantics, where you define how a probabilistic program might step to another program. There might be many different ways it might step because it's probabilistic. But this is kind of what I think of as semantics of programs and probabilistic programs. The second broad area I think is verification, where we're trying to wonder, how do you prove that a probabilistic program is correct? Right? So we would like to design ways to prove that these probabilistic programs satisfy certain properties. So these properties might be very domain specific. Maybe there's like a security property from cryptography, or like a privacy property from differential privacy, or something else. And our goal is kind of develop kind of reusable techniques to prove these properties across many programs, right? So ideally, your technique to prove a certain kind of property it's not just limited to one specific program. Ideally, you could reuse your technique to prove this property across many different programs. Okay. So, there are many, again, common tools from the PL toolbox. So at a more lower level of reasoning, you might use something like interactive theorem prover, like Coq or Agda. My use of lower level or high level is kind of idiosyncratic here, but these are very general purpose tools that can prove lots of different things about programs. By low level, I mean often they proceed in kind of small steps of reasoning because they're a very, very general purpose. There are also kind of higher level tools. Again, this is my terminology, such as like kind of type systems, for logics, and other custom logics, where you kind of reason somehow on the structure of the program. Like for a functional program, you might develop a type system. For an imperative programming language, you might develop a Hoare logic, like a program logic or something like this. Okay, so this is verification. Automation, I think of as being verification plus automation, right? So how do you analyze programs automatically, right? So you want to prove correctness or some kind of basic properties without human help about your probabilistic program. The benefits, you don't need human expertise, but the drawbacks is that often it's less expressive than more manual verification techniques. There's again many common tools like model checking, abstract interpretation, and many more that I'm not talking about here. And the fourth one, which I think is also interesting for probabilistic programs, is implementation, right? So how do you execute or run programs efficiently? So kind of executing a probabilistic program is not always easy, and this is especially in languages that support this conditioning operation that I'm going to talk about soon. You might actually need rather sophisticated algorithmic insights to actually even execute a probabilistic program. It may not be straightforward. This is especially the case for the second class of programmed applications I talked about, where you're trying to model something, right? So where the focus is not so much on execution, you're trying to model a very complicated distribution in computer code. So some common tools involving kind of the sampling algorithms that are from the machine learning literature. Again, I probably won't touch on these topics in today's course. Okay. So as I kind of mentioned, one of the important division I see in the kind of this field of probabilistic programming languages is whether or not the language supports conditioning or not. So I'm not going to talk exactly about what conditioning is at this point. I'll talk about it a bit later. But broadly speaking, if there's no conditioning in the language, then the semantics is more straightforward. It's simpler. It's easier to implement, and it's closer to executable code. So it's easier to run and imagine how you execute this program.
Is this conditioning in the sense of probability? Sorry.
Yes, in the sense of probability.
Okay.
Yeah.
I would imagine that's very important, right?
Yeah. So it's important in some cases and not important in other cases, I think. So for if you want to have executable code, it's rather unnatural to have a conditioning instruction. If you want to model a complicated distribution, then a conditioning instruction is very, very useful. Right? So that's one of the divides that I mentioned before. For our purpose, kind of verification automation is much more tractable when you have no condition in the language. And when you have conditional language, like I said, the semantics is more complicated. It's much harder to implement efficiently, but it's very crucial for modeling. So if you're trying to model some distribution, conditioning in the language is really important, and you really cannot avoid it. And verification automation are generally very difficult. at least in my experience. All right, so our focus in the plan, we can't cover everything. So our primary focus, this is reasoning about probabilistic programs. So our primary focus is verification. Right? So we want to, I want to give you an idea of some techniques you can use to prove properties about probabilistic programs. We're not going to be concerned with automation. So the techniques I outlined will not be, directly fully automated, though they are kind of an important step towards developing automated analysis. Kind of trying to do automation on top of this would just be too much. A secondary focus is going to be on semantics of probabilistic programs. Right? So I want to introduce at least 2 semantics for probabilistic languages. I'll say a little bit more about why I think this is important for this course goals. And we're going to focus on programs without conditioning. Okay, so this is the kind of first class of programs, the ones that are closer to executable code. This is just going to be simpler and will cover many practical applications. It definitely kind of falls short if your kind of application is trying to model a complicated distribution, right? I kind of think of that is also called probabilistic programming language, is what many people call the field. However, it requires a very different set of tools, I think, and verification automation are so much more difficult that I think it really deserves to be treated kind of separately. So I'll steer clear of that for this lecture, for this series of lectures. Okay, so I just want to say a little bit about why I'm also going to cover semantics. So this is a verification class, focus class, but semantics is the foundation of verification. Right? So semantics is a definition of the program behavior, like what a program is supposed to do. Verification, you're trying to prove that the behavior satisfies some target property, right? So kind of without defining a semantics of your program, then verification is largely meaningless because you're trying to prove something about program behavior. So if the program behavior is not defined, what are you even trying to prove, right? So another kind of, that's the first reason. The second reason is that semantics can have an impact on verification itself, right? So probabilistic programs are interesting because there are several natural semantics that are mostly equivalent, but not exactly. And the choice of semantics can strongly affect verification. Like it can affect which kind of properties are easy to prove or hard to prove. It can affect what kinds of things you can state about your program or not state about your program. So when trying to design verification technique, the choice of the program semantics can be really important. Okay, cool. So any questions at this point before I continue on?
I saw one that might be relevant.
Okay.
Akil Inderti again asks, does this verification notion that you've mentioned here require some form of metric or some way of determining how far apart 2 distributions are, or are you more concerned with exact?
Right. So I think that, again, either is kind of valid, right? So you might want to prove a property about your distribution. You might want to prove that these 2 distributions of these programs maybe are exactly equal. That might be a desired property you want. Maybe you're imagine some kind of compiler or program transformation on probabilistic programs. You want to show that it preserves the semantics of the program, which means that the output distributions before and after are completely equal, like exactly equal, isn't like mathematically they are the same thing. You might also be interested in approximate properties, right? So for many fields in security and privacy, exact equality is too much to hope for. But maybe you can prove that 2 distributions are within some distance, some metric property. So this is also a valid kind of property that you might be interested in proving about your probabilistic program. So I think the things I present will mostly be for the exact kind of properties, but I think of this difference as not being so important, I think.
Okay,
cool.
Sounds good. I think there's one more maybe. So what does it mean, Prasant asks, what does it mean if 2 programs have different semantics, or what does it mean to have different semantics from a probabilistic standpoint?
Right, so I think this I think I'm going to probably postpone until we see the semantics later on the next few lectures. It's a little bit difficult for me to answer in the abstract, but in a short little bit, the denotational semantics is supposed to model try to define the behavior of a program, right? So you might have different ways of defining what a program is supposed to compute. So one semantics might kind of record intermediate states, one semantics might not record intermediate states. So these are both different mathematical views on what a program is supposed to do. And neither of them is more right than the other one, because again, this is in the world of mathematics. they will model different, another way of thinking about it is that they will model different aspects of actual program behavior in the real world. So again, in the real world, program behavior can be very complicated, and there's many aspects. It's not just input output, maybe you have timing, maybe energy usage, all this stuff. You can't possibly hope to model every single thing with the mathematical semantics, but you might model different aspects of it. Maybe you model input output behavior only, you ignore everything else. Maybe you model input out behavior and timing, and you ignore everything else. You might model certain aspects of your program to try to get closer to what it's actually doing in the real world.
Thanks.
Cool. All right, so I'm going to continue a little bit by just saying about verifying probabilistic programs. This is the goal. What are the main challenges? I like to kind of motivate by this saying, like, traditional verification is often concerned with kind of big code and very general proofs, right? So you see often papers like this that we verify like 380,000 lines of code, or maybe we verify like hundreds of millions of lines of code, or maybe even like billions of lines of code. Like the more lines of code, the better. And this is certainly very important work and very difficult work. Randomized programs are a little interesting in that they also have very different characteristic when you want to verify them. So often the code itself is very small. So you might just be dealing with a program that's 3 lines long or 10 lines long. But the proofs can be very difficult or very complicated. So I often think that it's almost unthinkable that you would have like a 100-line algorithm that's randomized. It may, like, you could write down such a thing, but it would probably not be very useful because it would be so difficult to analyze even for a human that there would be no reason why you would want to even write down such a thing. And the difficulty is mostly in not scaling in lines of code, but trying to handle complicated proofs. So you might often kind of apply combinations of known and novel techniques. So you might sometimes the proofs and the techniques for constructing proofs themselves can be research contributions. So the trade-off is very, very different. So I want to kind of give an idea about what makes it difficult for these programs, like why is it so difficult for humans to kind of analyze their correctness. Short answer is I think that the programs themselves can be quite simple, often just a few lines, but the program states that are generated can be very complicated. So roughly speaking, you can think about these programs as manipulating distributions over program states. And the challenge is that each possible state has a numeric probability. Okay, so this is what it means to be a distribution over states, let's say. And furthermore, the probabilities of different states might be totally unrelated. Like usually there's some relation perhaps, but
what's the program state here? The program state would be the values of all the variables in the program, is it?
Sure, I think that's one way to think about it. There might be other kinds of states, but that's, I think, a good way to think about it for now.
Okay.
So yeah, that's what I'll think about for now. So just think about, I have a distribution over memories. Memory has, each variable has one value. Okay. Right. So for instance, like let's suppose I have a program with 10 Boolean variables, right? So, if it's a non-probabilistic program, there's kind of 2 to the 10 equals like roughly 1,000 possible states. All the combinations of these 10 Boolean variables, what are their values? A probabilistic program has kind of these states, plus each state also has a numeric probability, right? And so you have 10, 24 possible states versus kind of uncountably many different states, because there's many different distributions, like uncountably many distributions over these states. And if you want to try to prove a property about this distribution over states, you somehow have to know something about these probabilities, right? You can't just say, oh, it's some probability. Okay, so of course, this is only a really rough comparison, because when you verify a program, often you don't enumerate all the states. There's just still too many states, even if it's a deterministic program, like a standard program. You would not try to go through all of these 2 to the 10 possible states or way more states and try to try them one by one. So another challenge is that the properties themselves are fundamentally quantitative, right? So you might think about probabilities of different events, like probability of failing, return the wrong result, or you might talk about kind of the average value of a randomized quantity, like a running time or something like this, okay? And furthermore, you can't just ignore the probabilities, right? Because the target properties you care about are quantitative. So one common idea to simplify verification is to ignore parts of the state. So you might like to say, well, I have this probabilistic state, but I'm just going to treat the probability as either 0 or non-zero. So essentially saying, is this state possible or impossible? And that's all I'm going to care about. Then I don't have so many states to kind of think about when verifying. But So it simplifies verification. But then I can't prove many common properties, right? I can't talk about expected running time. I can't talk about what is the probability of an event. All I can talk about is whether a state is possible or not possible. So that's much coarser and maybe much less interesting. Okay. So in the sense, like what is needed is like we need to have good abstractions for probabilistic programs, right? So an abstraction, again, this is my terminology, my intuitive terminology, not a formal definition. It's a technique for us to discard unneeded aspects of a program state or behavior. So the program state is really, really complicated. We can't possibly model exactly what is the distribution on all of this stuff. So I want to forget a lot of information while still retaining enough information to prove the target property I care about. Right? So, here's kind of, a picture of kind of, album cover from Miles Davis, and under like varying levels of abstraction, where the top left picture is like kind of the original picture. And then as you go down to the right, you forget more and more information about the original picture, right? So, in the later on pictures, you have less information about the original thing, but you still have a little bit of information, and depending on what your application is, it might or still be enough for you to kind of prove some property about your probabilistic program. So, here are a few things that you would like for these abstractions. So the first one is that you want to retain enough information to show the target probabilistic property. Like if you forget all the information about your probabilistic state, then you can't prove anything, and that's not so useful. You can't verify any property of your program. It would also be good if your abstraction is kind of easy to establish, or at least not too difficult. Right? If it's very, very difficult to even prove that your program satisfies some abstraction, maybe it's even more difficult than proving the target property, then you really haven't gained very much. And the third kind of goal is that you would like this abstraction to behave well under program composition. Right? So we're going to constantly emphasize kind of what's called compositional reasoning, which means that you would like to kind of prove a larger program by focusing on the small subparts, right? So this is a common program verification principle, and it's still important for probabilistic programs, even though the programs themselves are not so large. Okay. All right. So I just want to. This is kind of the motivation part. It kind of took a little longer than expected, but that's totally fine. I want to next get into some mathematical preliminaries and give you kind of a taste of the programming language that we're going to be working with. But before I go on, are there any questions at this point?
I think there are a few, but I think there's also some speculation that you'll cover them in the next.
Okay, cool. Let's see. Okay, so mathematical preliminaries. As I mentioned, we're going to be covering also some program semantics. So I want to kind of introduce some very basic concepts about distributions and things like this. So this part might be a bit dry, but try to pay attention, because I'll also remind you of these definitions as we go on when we use them. But this is kind of an overview of distributions and different constructions on distributions that are going to be useful for our purposes. So distributions and subdistributions. So, for the purpose of this lecture series, I want to model distributions in a very simple way. So I want to say that distribution over a set A is simply a function from A to 0, 1, okay, from A to the unit interval, with the property that if I sum over every element in A, I sum like mu of A, that with the weight of every element in A, I'll get equal to 1. Okay, so here in A is going to be, say, a countable set. I'm trying to keep things as simple as possible without kind of any complicated measure theory. So, mu is a function that assigns to each possible output a probability. So here I'm not talking about programs or anything. This can be distribution over Booleans, over numbers. It can be over anything, any countable set. For modeling kind of programs of non-termination, it will also sometimes be useful to have subdistributions. This is exactly the same thing as distribution, except when I sum up the weights, I'll get something that's at most 1. So it might sum to something less than 1. Of course, it'll be bigger than 0 still, because all the weights are non-negative, but it might not be equal to 1. Exactly. So kind of, it might be useful to say that the kind of the missing mass, the shortage between the total weight and 1, that is the probability that the program itself does not terminate. So that might be what you would use that missing mass for. But again, here we're not talking about programs yet. Okay.
Dark matter, basically.
Sorry?
Dark matter, dark matter.
Dark matter, yes. Yeah. Missing. Running forever. Okay, cool. So here are kind of a few examples of distributions I'm going to return to throughout the lecture. So the first one is a fair coin flip. This maybe is the first random distribution most people come across. Like you flip a fair coin, you get heads or tails, which are called true or false, because it's a PL course. So it's a distribution over Booleans. It's a fair coin flip, which means the probability of having true is the same as the probability of having false, right? Which will be 1/2, because both of them must sum up to 1. Okay, so we write something like this, that mu of true equals mu of false equals 1/2. So TT and FF are my notation for true and false. Okay. All right. Likewise, you might have a biased coin flip. So someone gives you a coin that is kind of loaded, that if you flip it, it often comes up one side rather than the other. So maybe I have a biased coin flip, well, which I'll write kind of flip and then the bias. So here's a one quarter biased coin flip. Again, it's a distribution over Booleans, true and false, heads or tails as you like. But the 1/4 means that there's a 1/4 chance of it coming up true. And which means that, of course, it must have a 3/4 chance of coming up tails or false. Okay. So this is a biased coin flip because you have a different probabilities of coming up with true or false. They're not both 1/2. Okay, and to kind of introduce another kind of distribution that is going to be some numeric distribution. These are both kind of over Booleans, or like a distribution over numbers. I'll consider just a simple dice roll. Okay, so I'll call roll. This is a distribution over, let's say, the natural numbers, 0, 1, 2, whatever. But really, it's only over the numbers 1 through 6. Okay, so mu of 1 is equal to mu of 2 all the way to mu of 6, and each one has probability 1/6. Right? So you have 1/6 chance of getting 1, 1/6 chance of getting 2, and so on, all the way up to 1/6 chance of getting 6. Okay, so 6 possible actual values that might come up, and they have equal probability. It's a fair dice roll. Okay.
Just a notational question.
Yeah.
The congruence or the equivalence sign, your definitional equality.
Right. So yeah, sure. So this kind of like a triangle equal sign in LaTeX just means I'm defining something to be the left thing to be the thing on the right. Let's say. Yeah.
Thanks.
Hope that makes sense. I try to stick to that. Probably going to slip up somewhere when I forgot to put it, but yeah. Okay. Cool. Great. So we're going to use some notation for distributions throughout. One basic notation is for the probability of a set of things, right? So if I have a subset of A, I'm going to call it E. E is for the word event. And let's say that mu is going to be a distribution over A. So often use the letter mu for distributions. Then the probability of E occurring in mu is going to be written mu of E. And this can be defined to be equal to the sum of the probabilities of everything inside E, right? So again, this is hopefully not too earth-shattering. I have a set of possible outputs I care about. Mu of X is going to be the probability of X. So I'm just going to sum over all the probabilities of all the things I care about. Okay. All right. And another one we'll use occasionally is for expected value for computing averages. So here I have a distribution mu, and I have a function f that maps each possible outcome to a non-negative real number. If you like, it could be a number between 0 and 1, or it can be non-negative real. Then the expected value of f and mu, I'm going to write using this notation here, this expected value notation, right? So the expected value of x drawn from mu of f of x, this is going to be equal to this kind of weighted sum, right? So I'm going to multiply f of a by the probability of a occurring and sum over all the a. So this x here should be an a, actually. Okay. All right. Okay, so some notation. So the next few slides, I'm going to go into some operations on distributions, right? So we're going to be interested with kind of constructing and building distributions, combining things together. So I'm going to start with maybe the simplest possible distribution, which is what I call the Dirac distribution. So this is a distribution that has probability of 1 of producing a particular element and probability of 0 of producing anything else. It's kind of like a deterministic distribution that always returns the same thing.
Oh, it's not really a distribution, I mean.
So it is a distribution for the purpose of this lecture.
If you're a physicist, okay.
Yes. So again, being loose with the notation, if you look in certain textbooks, maybe this is not exactly the same thing, but I will call this kind of the Dirac distribution. Okay, so it's also known as the distribution unit. So here, let's say let A be an element of this big set big A. Probably shouldn't be using this notation. Then this distribution, which I'm going to call unit of A, is defined to be this thing here, right? So it really should be a definitional thing here. But unit of x is going to be 1 if x is equal to a. Otherwise, unit of x equal to be 0. Wait, sorry. This is again a typo. This is sorry. This is unit of a of x. Sorry for all the typos. So the idea is that you produce X, the idea is that you have weight 1 on an element X if it's equal to A. If element X is not equal to A, you have a weight 0. Okay, so you have probability of 1 of producing A and probability of 0 of producing anything else. Okay. So the word unit is meant to, this is reference to the fact that there's a monad structure on distributions, and this is kind of the return or the unit of the distribution monad. If you haven't seen monads before, this is totally fine. I won't really rely on any of the stuff. It's just for those of you who are curious. Okay, does this make sense? So there should be
you should probably, just one thing, I mean, just to prevent confusion, since your space is discrete, I suppose you could call it, I mean, but it's yeah, I mean, the space, your probability space is a discrete space, right? It only has a discrete number of possibilities, or a finitely countably finite number of possibilities. Right, your space A, your capital A.
Yes, yes.
Yeah, so therefore it's not actually the Dirac delta. Yeah, fair enough. Okay. Sure. Yeah, so it could lead to confusion to people who are trying to read from online sources. That's why.
Right. This is the Dirac delta on a discrete space. Yes.
Yeah. So then it's a standard distribution.
Yeah, indeed. Okay. Second operation that we have also on distributions, if we're kind of mapping a function over a distribution. Right. So the rough idea is that this operation takes a distribution and a function. And the idea is that whenever I sample X from the distribution, I want to make a distribution that I sample f of X from instead. So I have this transformation map F that goes from A to B. It's a deterministic map. Every element A goes to exactly one element of B. There's no randomness involved here. And then the distribution map operation says that if I have a function F from A to B, then a map of F, which goes from distribution over A to distribution over B's, takes a distribution over A into this kind of funny distribution, right? So this kind of thing says that the probability of kind of seeing B is going to be equal to the sum of the probabilities of everything that maps to B under F. Okay, so I'm summing over all the A's that have f of A equal to B, and what is their probability? And that's the probability of seeing B. Okay, this makes sense. Yeah. We'll see an example. Maybe that will help make things a bit more clear.
In the previous slide, shouldn't it be mu of F? Isn't B an element of B?
B is an element of B, indeed. And map of F takes mu.
On the right hand side. Yeah. If mu is a map from A to bool and B is an element of capital B, how does the map?
No. Mu is a map from A to real number.
Okay, yeah, but the element
point is mu of B. Mu of B. His point is mu of B. You've defined what do you define mu of B as? Right? That's the point, right, Akhil?
Yeah. I'm just saying that small b is an element of capital B, but mu is a map from A to 0 to 1.
Yes. Sorry. Okay. Yes, indeed. This should be mu of A. Sorry. Indeed, okay. You're right. Yeah, okay. Good catch. Okay. Thanks. Yes, good. I'm sure there'll be many more typos. I hope not too much anymore. But please let me know if you do see something because I have a lot of slides. Okay, cool. Good catch. Right. So here's an example of using the mapping operation where I have a negation map. Let's say from bool to bool. This maps true to false and false to true. And then I want to kind of map the negation function over this bias coin flip. Right, so I'm going to say mu is going to be a map negation function over the bias coin flip. This is roughly going to be, if you think operationally, it means you take a bias coin flip and then you apply the negation function on the result. Right, so if you sample true, now you see false. If you sample false, now you see true. And then you look at the distribution over what happens after that. Right, so if you apply the definition of map, you'll see that if you map the negation function over this bias coin flip, you really get the bias coin flip on the other way. Right, so you have kind of 3/4 chance of seeing true in the end, and 1/4 chance of seeing false. Okay. So some of these places I'll put these like try this at home kind of things. These are kind of basic checks, sometimes not so basic checks. If you're interested in this, you could try to kind of do this kind of thing just to make sure you understand the definitions and how these things are being used. Okay, totally optional. All right, the next operation distributions we're going to need is called bind. So the rough intuition is that we want to, this operation is going to sequence two sampling instructions together. So roughly speaking, this is going to let me draw a sample X from some distribution, and then draw a sample from another distribution f of X, where kind of this f of X depends on X. So you can see by the notation. The main difference between mapping and binding is that the distribution map kind of f is randomized. So it's a function from A to distributions over B. So you can think about it taking in some element A and giving you back a distribution over B's. Okay. So formally the distribution bind is kind of defined like so. So I have initial distribution over A's, and I have a binding function f, which goes from A to distribution over B. Then the bind operation combines these two things together into a new distribution over B. So I'm kind of sequencing together these two parts. First I sample from A, then I apply F, and I sample from the result of F. Okay. So this bind operation is defined to be this kind of mathematical quantity. In the next slide, I'm going to kind of try to unpack what this thing actually means. So, this is the thing again. So the thing on the right, it can be understood as a few steps, right? So this mu of A is, So on the left, I'm trying to calculate the probability of sampling B from this bind distribution. I'm saying this probability of getting B is equal to the probability of sampling little a from mu, that's mu of A here, times the probability of sampling little b from f of A, which is the probability f of A of B. That's this thing here. And finally, I want to sum over all possible intermediate samples, right? So the first outcome, the first outcome of mu of the first step could be any element A in big A. And kind of no matter what it is, I have some probability of seeing that thing. And then I want to say, given that I've sampled little a, what is the probability of then seeing B in the second step? Okay.
I'm sorry, wasn't small f a deterministic function from A to B, set A to set B?
Right. So in here, f is no longer a deterministic function. So for binding, the transformation map is going to be randomized. Right. It's a function from A to distribution over B.
Oh, okay.
In the previous slide, when I was doing mapping, f was a deterministic function, but for bind, it is not a deterministic function anymore. That is the main difference between kind of map and bind for our purposes here. Okay. So f is definitely going to be randomized.
It is okay. Yeah. So it's right. It's not the case. We're not looking for f of A equal to B here. Not at all.
No.
Right.
No, f of A equal.
So is it like a conditional, essentially, is it like a conditional distribution in some sense? This FA of B is essentially like a conditional distribution of getting small, given that you've obtained small a?
Yes, you can think about it. There are some connections between this kind of functions f and conditional distributions. I think I don't want to get into that too much. I think it would take us too far afield, though I'm happy to talk about this more offline. You can think about it as kind of it's often called a conditional distribution. Yes, yeah, there are definitely close connections there. Okay, but here I want to think about it purely operationally. Like you do the first thing, then you look at the result, and then you sample something else.
Right.
Okay. You want to think about it in terms of conditioning. Exactly.
Okay. Thank you.
Okay, cool. So some examples.
One thing on the left-hand side, the bind mu FB, is that a measure? That's a measure, right? Bind mu F is a measure.
Bind mu F is a distribution.
It's a distribution, and you're computing the value of that on B.
Yes.
Essentially.
Yeah.
Okay. Yeah. Great.
Everything here can be done also for measures and things like this. I'm trying to keep everything as kind of standard as possible, and just thinking about functions from A to like 0, 1.
You can also think of the RHS as a kind of averaging process over the average is being given by mu of A, right?
Yes, you can think about it as an expected value of some kind as well, but yes, that
it
is
gives intuition. It gives intuition. That's what I'm asking these questions. Thank you.
Great. Sounds good. Okay, so some examples of distribution bind. One example here I'm going to give is kind of summing two dice rules. So let me see. So for any kind of natural number n, let's suppose that f of n is going to be a distribution over natural numbers, and it's a distribution of adding n to the result of a fair dice roll, which I called big roll. Okay. Then if I bind the distribution here, I bind roll into f. This is the distribution from kind of rolling a dice, looking at the number, and then rolling another dice, and then summing the two together. Okay, these are two separate kind of independent fair dice rolls. So if you kind of look through at the definition of bind I gave on the previous slide and just work it out, you can figure out what is the property of this mu, like what is this mu. So for instance, like the probability of kind of seeing the number 2 is going to be 1/6 times 1/6, which is 1 in 36. And you can likewise kind of carry out this computation for the other things. Arthur has a question.
Oh, sorry, that was an accident.
Oh, okay, no problem. Sounds good. Yeah, feel free to raise your hand if I see it. I will try to call on you, but no guarantees that I can see. Okay, so some stuff you can try at home if you're interested in trying to practice with these definitions. Okay, so here we get to conditioning. Here I'm going to just present the definition of conditioning, even though we won't really be using this very much until kind of the third lecture, or maybe later on. Here,
sorry to interrupt. One question again, if you don't mind. This bind mu comma f is an object of the same kind as mu, right?
Yes.
It's an object of the same kind. Yes. Thank you.
Yeah, that's right. Right. Good. So for conditioning, the idea is that you want to restrict a distribution to a smaller subset. Okay. So I have a distribution over A's, and then I assume somehow that the result is going to be in E, which is a subset of A. Okay. I'll give another concrete example that hopefully makes this a little bit more understandable. Then the question is like, what is the probability should we assign to elements in A if I know that the result is going to be inside E actually, and not just inside A? So distribution conditioning is defined something like this. So I have a distribution over A's here, I'm calling it mu, and I have E, which is a subset of A. Then mu conditioned on E is the distribution, still thinking about it over the same set. But it has this notation here. So this is the distribution, and the probability of seeing A is going to be mu of A divided by mu of E if A is in E. Otherwise, the probability is going to be 0. Okay, so the idea is somehow that I have a distribution over A's, and now I assume that the distribution will give me something inside E. So what is the relative likelihood of the things now that I assume that it's going to be inside E? So this only makes sense if mu of E here is not 0. Otherwise, the conditional distribution is not defined, at least not in this simplistic way. Okay. All right. So the reason I kind of introduce is that we'll kind of use this later, but also some languages, many probabilistic programming languages have a special command which lets you condition on an event. It will have a special command where you can actually say, now condition on this event being true. This seemingly small addition to the language introduces a lot more complexity, also unlocks a lot of other very important applications. But we're mostly going to be steering clear of that because we're trying to stick closer to verification. Okay. But that's an important thing to be aware of. So the concrete example I'm going to give is kind of rolling a dice until you get an even number. All right, so you have this fair dice, and I'm going to repeatedly roll the dice until it produces an even number. And then the question is kind of what is a distribution over even numbers will we get? Right, so initially you have dice that gives you 1/6 chance of giving 1 or 2 or 3 or 4 or 5 or 6. Now a condition on kind of the event that the output is going to be actually even. So a little bit more detail, the event here is going to be 2, 4, 6. These are now the things I'm assuming the result is going to be 2, 4, 6. And I have the conditional distribution. The result of this process is going to be roll conditioned on E. And if you apply a definition of conditioning, you will see that the conditional distribution has mu of 2 equals mu of 4 equals mu of 6 equals 1/3. Right. So now kind of 2, 4, and 6 have higher probability, but they still have the same probability because initially they all had the same probability as well. But in general, kind of conditioning can really change the probabilities. In here, they went from 1/6 to 1/3, but in general, they can make the distribution much more complicated and much more difficult for verification and reasoning. Okay. All right, this is conditioning. Just have 2 more to talk about, and then we can talk about some programming languages. Okay, so one more that we're going to use later on is a kind of convex combination of distributions. And this operation I think of as kind of blending or mixing 2 distributions over the same set. So I'm supposing we have 2 distributions, mu1 and mu2, over the same set, call it A. Then I can blend the distributions. So I can say with probability P, I will draw something from mu1. Else with probability 1 minus P, I will draw something from mu2. Okay, and then I would say this kind of blends together these 2 distributions into one. More formally, I have 2 distributions, mu1 and mu2, and some probability P, which is some number between 0 and 1. Then I can take the convex combination of mu1 and mu2. I'm going to denote it by this kind of O plus kind of thing here, this plus with a circle. So the chance of getting A inside this kind of blended distribution is P times the chance of getting A in the first distribution plus 1 minus P times the chance of getting A in the second distribution. So in the simple case where P is equal to 1/2, I'm kind of averaging the two distributions together. But in general, P could be something that's not 1/2. So it's a weighted combination of two distributions over the same set. Okay. A quick preview for why this is interesting is that often this kind of operation is quite useful for modeling kind of probabilistic control flow, where you maybe have an if statement and you branch on something that's randomized, and you end up with two different distributions at the two branches, and now you need to combine them together. You need to blend them back together into a single distribution. Okay. So conditioning can be used for modeling kind of control flow splitting, and convex combination can be useful for modeling kind of combining control flow coming from different parts. Okay, but we'll see more examples of how this works later on. For now, I can blend two biased coin flips. Maybe I blend a coin flip that's biased 1/4 with a coin flip that's biased 3/4. Again, you can kind of check from the definition of mixing that if I blend these two distributions, I'll get a fair coin flip. Okay, just by again unfolding definitions and kind of computing what is the probability of getting true and what is the probability of getting false. Stuff you can try at home if you're interested. Some relationship between mixing and conditioning. Again, this is solely for your curiosity. Okay, so the last operation on distributions I'm going to put in here, and then we can move on, is kind of the independent product. So this kind of operation is useful for modeling kind of independent or fresh samples. So many probabilistic programming languages have a command where you can say, now take a fresh sample or like make a fresh coin flip. So this independent product can be useful for modeling what it means for a sample to be fresh or like independent. Typically, when I make a separate sampling statement, I expect it to be kind of uncorrelated with everything that came in the past, right? If I write a program that has two coin flips, I somehow expect that the second coin flip is kind of a fresh one, right? It's not just going to be the first coin flip again. Somehow it's generated from some other source of randomness, right? So an independent product is, one way you can think about it is as kind of combining two distributions into a distribution on the product. So I have a distribution over A1, I call it mu1. I have a distribution over A2, and I call it mu2. If I take the independent product of the two distributions, I'm going to get a distribution over pairs in A1 and A2. Okay, and the probability of A1, A2, kind of two elements, is just going to be given by the product of the probabilities. So the chance of seeing, the pair A1, A2 is going to be the chance of seeing A1 under mu1 times the probability of seeing A2 under mu2. Okay, so there are two independent samples somehow. Okay.
Do we have a constraint that A1, the capital A1 and capital A2 are subsets of the same A?
No, not necessarily. I think, yeah, not necessarily.
Okay.
So not the way I've set it up, I suppose. So this is just the product of sets. So they can be, yeah.
Oh, I think I was just a bit confused about. So when you're talking about the intuition of two fresh samples, are we saying that these two samples are from the same distribution over the same space, and they should be unique, meaning they are different from each other, or in what way are we talking fresh?
Right. So that's a good question. Like, what does it mean for a sample to be fresh? I mean, kind of, I'll just be informal and kind of try to give intuitive description here. I mean intuitively that the second sample doesn't depend on the first sample. I think more formally, you would try to say that the second sample is probabilistically independent of the first sample.
Are you just saying that a joint distribution is a product of the distributions, individual distributions?
Yes, you can say that, yes.
Right.
Yeah, but kind of back up a little bit. This A1 and A2 don't, here in this definition, I'm not going to assume they're kind of subsets of the same thing or they're any way related at all, right? So one might be Boolean, might be natural numbers, whatever. You're right that in applications, you generally consider more specific sets. Yes.
If you were to go about verifying this property, do you need, like if A1 and A2 are generated by two different random number generators, do these need to be true random number generators?
Right, so I think the verification that we're mostly going to be considering, we're going to treat these programs in a very idealized manner. Okay, right? So I kind of already, well, this is a very good question. I think here I'm thinking about having distributions over elements, having a source of randomness and things like this. I'm not talking very much about how to implement this actually on a realistic computer. Right? So on a realistic computer, there's many, many other considerations. Do you have a true source of randomness, right? Like how good is the source of randomness? Maybe more philosophically, like what does it even mean for a randomness source to be good or not? Like how do you even define that? And there's interesting questions there as well. But I think for the purpose of this lectures, we're going to be staying at kind of a higher level where we're going to be dealing with a very idealized program and trying to prove properties of the idealized program.
Thanks, yeah.
Okay, cool. So I'm just going to give an example of independent products, coin flips and so on. Are there any questions at this point? Because I think in the last 15 minutes or so, I want to kind of give, a view of our first probabilistic programming language, give you a brief preview, and we'll talk about the semantics of this thing kind of next time. Are there any questions at this point?
I don't see any in the chat.
Okay, cool. Sounds good. All right, so in the last bit, I want to kind of briefly introduce just the syntax of our first probabilistic programming language, which is probabilistic while, also known as p-while. So in a nutshell, p-while is a very simple imperative programming language, also called a while language. It has imperative constructs like assignment, sequencing, if then else, while loops, the main ones. And the main extension that p-while...
Don't we hate imperative languages? Sorry.
Sorry?
I'm just curious. Just partly fun, partly facetious, but partly serious. You said it's an imperative programming language, right?
Yes.
I mean, obvious question is, maybe it's not the right time, but are there functional probabilistic programming languages?
Yes, there certainly are functional probabilistic programming languages. This is something I may talk about more in the last lecture.
Okay.
But yeah, for now, we're sticking with just imperative.
I was just making a facetious comment that we hate imperative.
No, I think I expect this question given that it's OPLSS. But right. Yes, we'll stick with imperative or so-called first order programs for now. You could think of yeah. I think it's a very fair question, and the answer is definitely yes. We'll see. We'll have time to cover much of that. Let's see. So right, the main extension for p-while is that we have a command for random sampling, which I'm going to write something like this. It's like this is kind of an assignment command with the $sign on top, that or S for sampling, if you like. Where D is what is known as a built-in distribution. So D is some distribution which might be like a coin flip or like a dice roll or something fancier, and you can sample from it and store it into variable X. Okay, this is the main extension that takes the while language to p-while. Okay, so I just want to kind of maybe show a bit of like example programs and have you figure out reading this thing, you probably have an idea of what this program does. Can someone tell me what they think this program does?
Sums the result of rolling 2 die.
Yeah, great. So this thing should be read as kind of you roll a dice, you store it into X, you roll another dice, you store it into Y, and then you sum the two results, X plus Y, and store it into Z. Okay. We'll later on make this formal about what this actually does and what is the distribution and all this stuff. But I just want to show you some examples to give you an idea of like what these programs look like, and you can usually figure out what these things are supposed to do, even if you don't know yet exactly how to formalize what is going on. Okay, so in p-while, it looks quite simple, but it can be quite complicated because even in the small language, kind of control flow can be probabilistic, right? So by that I mean kind of in a branching command, like an if then else or a loop, it can depend on random samples. This is the challenge for verification. For one thing is that you can't do just a simple case analysis. Kind of in imperative languages, if you've seen verification techniques, it's often useful to do a case analysis where you say on this if then else, either I take the true branch or I take the false branch. I can't take both branches, right? Like either the condition is true or false. But in p-while in probabilistic languages, if your control flow is probabilistic, in some sense, your execution is really taking both branches, right? So, or like the contribution from both branches is important. Right? You can't just say, I'm only going to take the true branch or only the false one, because it might have some chance of taking the true one and some other chance of taking the false one. Right? So I can't just eliminate one half by doing that case analysis. So, right, so can you guess what this program does? We've already kind of seen this program before, actually, but just in words, not written out in code.
So it melds the probability first. I'm guessing the first flip is fair flip. It could be non-fair also. After that, it gives you two different coins, one with a bias of 1/4, the other with a bias of 3/4.
Right, right. So yeah, this exactly is kind of the program I was saying in English out loud for kind of the convex combination of two bias coin flips, right? So this coin flip here is going to be fair. So whenever I write flip without any parameters, I'm going to assume it's fair. Okay, that's my notation for fair coin flip. I didn't want to make another name of distribution. Yeah, so this is the same thing as flip of 1/2, but I'll flip the 1/2 is implicit, let's say. This is the convex combination of these two distributions, like flip 1/4 and flip 3/4. So what I said before is that at the end of this program, the distribution of the variable result is going to be a fair coin flip. It's going to be half chance true and half chance false. Okay, which maybe obvious from this program, maybe not obvious. But something that you could certainly try to prove about this program, okay, if you actually define the semantics and such, as we will do. Okay, and kind of extending on previously, another challenge is that in PWAL, the loops themselves can also be probabilistic, right? So for instance, the number of iterations itself might be randomized. Termination can be probabilistic. You might have this kind of missing mass kind of thing, where you have some chance that the program doesn't terminate, but still some chance the program does terminate as well. So maybe the program only terminates half of the time with half probability. Okay. So here's an example of a loop with a probabilistic termination, or rather with a randomized termination, let's say. So this program is going to repeatedly kind of flip a biased coin. And it's going to kind of stop as soon as it sees the first true, right? As soon as the coin comes up heads or true, it will stop. And kind of this counter here, T, is going to count how many steps the program has executed. Okay. So this is an example of a program. It turns out that this program is going to terminate with probability 1. It always with 100% probability. However, the number of iterations itself is randomized, right? So it's not that the program always executes 5 iterations or 10 iterations or whatever. There's kind of a distribution on the number of iterations this thing is going to execute, which can be seen because there's a distribution on the final value of T. There's some chance you execute immediately. There's some chance you execute immediately, which gives you T equals 1. There's some chance you execute after 2 iterations, which will give you T equals 2, right? You have a distribution over the values of T. Okay, question?
Yeah, I had a question. How did you say that it will terminate? I mean, how do you prove that or conclude?
Right. So yeah, I just made that claim without proving it. It is not hard to prove it as well once you have a semantics and all of this. But it's a known fact, let's say, that if you have some kind of process that has kind of positive probability of terminating at each step, then it will terminate, as long as the probability of termination is bounded away from 0. So in this case, there's a probability of 1/4 of terminating at each step. Then it is known, or you could prove that you can try proving this yourself if you're motivated or interested in this, that any kind of process that has probability 1/4 of terminating every step terminates with probability 1. Okay, it may take arbitrarily long, but somehow it will terminate with probability 1.
Oh, I see. Yeah, it's a GP, so it would sum
Yes.
up to 1. Yeah.
That's right. Another way of seeing if you know a little bit about randomized processes, that this is going to be a geometric distribution as well, and so the final T is going to be generated from a geometric distribution, but that you don't need to know. Okay, let me see. So I think I have just maybe 5 minutes left. Just probably a good time for me to start kind of stepping through the syntax of the programming language. Actually, I'm not sure if I really want to be doing this right now. Are there any other questions at this point? We don't have to do the syntax right now. We could do it next time also, but any questions? Questions, concerns? Okay, let's start with the syntax and see. Okay, so the syntax of the programming language PWAL is very similar to the syntax of the programming language while, the simple while language. If you haven't seen this before, it's totally fine. I'm going to try to introduce things step by step. So the language is built up in a bunch of layers, right? So the most basic layer is a layer of expressions. So these are not programs or commands. They're not like if, then, else, or while. they are kind of things that represent Booleans or things that represent numbers, let's say. So I'm going to keep things simple here and say our expressions can be either Booleans or numbers. So the expressions that we have, I'm going to use a little letter little e, represent an expression. It's either going to be a variable, like little x, or it can be a Boolean, just like, true or false. These are two Booleans. Or I might, compare two numeric expressions. One is bigger than another. This is a Boolean expression, assuming that these two things are actually numbers. Or I might compare two kind of things for equality. This is again another Boolean expression in this language. So these are, examples of Booleans. The third row is examples of expressions that are numeric, right? So I have numerical constants like 0, 1, or 2, or whatever. I can have an expression that's the sum of two expressions, like 1 plus x, like 1 plus 2, or the product of two numbers, 1 times x, 1 times 2. These are all kind of valid expressions inside this language PWOW. Okay. So I'm kind of sticking with a kind of a basic expression language here. This language can be extended if needed. We just want to have these kind of two kind of things. And I'm going to assume throughout that the expression language is simple enough that you can easily check if a program is only using well-type expressions. So I'm going to, whenever I have this kind of expression in a program, I'm just going to assume that you've already done some kind of check somehow to make sure you're not trying to compare whether a Boolean is bigger than another Boolean, or you're trying to add two Booleans or something like this. That's kind of nonsensical. I'm going to assume that you can already kind of check and just eliminate these kind of faulty programs automatically, or pre-process them somehow, so we never have to deal with them. Okay. All right, so these are expressions. Questions about expressions?
If you add like a simple distribution, is this like a probabilistic circuit? Is there something here
right.
that?
Okay, so this is a good question. We'll see more when we look at the semantics. For now, the expressions I'm thinking about, these are not going to be even probabilistic. So don't think about it as being probabilistic. Like none of these things represent probability distributions. The way I think about it is that each of these expressions can be interpreted inside a single memory, not a distribution of memories. You should be able to give a meaning to each of these things by looking at just a single memory. Okay.
I see. Thank you.
Yeah. So yeah, don't think about this being as a distribution over numbers and comparing distributions over numbers. You're really just saying like, this is a number, like an actual number, and that's another actual number, and are they equal, or one is bigger than the other. And don't think about trying to compare distributions for inequality and stuff like this. Okay, so, okay. I think, the next step we'll introduce kind of the primitive expressions. I'm missing a bar here, unfortunately. So these are things I'm going to be calling distribution expressions or d-expressions. Okay, so these are expressions still, but they represent a distribution over things. Okay, so here I have a fair coin flip. This is one kind of distribution expression. I have a biased coin flip, p-biased coin flip, and I have a fair dice roll called roll. Okay, so I kind of think of these expressions as being built-in or primitive distributions. Again, there's nothing very special about these three particular distributions. You can extend this with additional distributions if you like, right? So you can have a geometric distribution, you can have a normal distribution, at least if you extend the semantics to allow distribution over uncountable sets. You can use your favorite like mathematical distribution you can build into this language. The point is that these are kind of primitive things that you expect to be able to sample from. So there's many kind of choices that you might want to add depending on exactly what kind of probabilistic program you're looking at. Okay. All right, so I think we're kind of out of time. I'd rather not talk about the statements right now. I think it's probably best to pick up that next time because that's really the heart of the PWOW language. So I think next time we'll continue talking about PWOW, introducing the syntax, and we'll start getting to our first semantics and our first way of proving properties about these programs. Okay, so I think for now I'm going to stop. I'm going to stop here. Thanks a lot. If there's any questions, I'll be around for a few more minutes, or right in the Slack.
Maybe I could get started with the questions, maybe. So I'm curious. So you kind of talked a little bit about these properties of functions, whether you want to compare them approximately or verify them exactly, and we also talked a little bit about program structure. So how your program is imperative, and it has this control flow, and it has these sequential steps, temporal
Sure.
dependence. So I'm curious if you're going to talk about this duality, intentional and extensional equivalence for probability distribution, or is that something that arises in probabilistic program verification?
Yeah, it's a really good question. I think I honestly there's a big difference between intentional and extensional semantics for distributions for probabilistic programs. I always get the difference confused though, to be honest. I remember one of the semantics is that you view the randomness as being an input to your program. Somehow that you have maybe kind of, perhaps you pretend that your program has like kind of this tape that is the input, that is a sequence of kind of maybe zeros and ones that are drawn randomly. And then the program, whenever it makes a sampling command, it looks at something on the input tape and says, oh, the next result is going to be 0 or 1 or whatever. I forget that that's intentional or extensional. Maybe that's extensional, not sure. I think for purpose of this course, we're mostly not going to take that perspective. We'll think about more as just these programs transform distributions. I'm not going to assume there's a tape of like results of random samples that is provided to the input. I think that is also interesting perspective on randomized programs, the different way of modeling their behavior mathematically. I'm less aware of verification techniques that kind of use that perspective on probabilistic programs, though for certain things for certain things it can be interesting to kind of assume that the randomness is given as input to the program. This is probably something we probably won't get to, but maybe we'll, I don't know. If you assume that the randomness is given as input to your program rather than being generated by your program, you can do fancier things, like you can maybe start to transform the input. You can say, like, what happens if I take the randomness in the input and I somehow do something to it? What happens to the program then? I can make this kind of statement, like I replace a perfect source of randomness with an imperfect source. Then maybe I want to say, does the program still behave similarly or not? It's kind of difficult to kind of state these properties with, or prove these properties with the kind of semantics that I'm going to present in the next few lectures. But it's also an interesting kind of property, of course.
Yeah, I know cryptography, right? Like that's something that they care about a lot, is indistinguishability. That's
right. So I think this is one example of how like the kind of semantics that you choose for your probabilistic program can have a big impact on what you can verify. Or with certain kinds of semantics, you simply cannot really. It's really hard to say like what does it mean to replace the source of randomness with an imperfect source if the semantics doesn't even mention the randomness somehow. And depending on what kind of semantics you choose, it will impact what things you can verify or not verify. This is one good example, I think. Yeah.
I have a question. So it's essentially the same question that I asked you during the lecture. Why does the reason why we like functional programming and proof resistance, because you can apply all these mathematical techniques to prove stuff easily, comparatively, and verify programming, right? Now, when you say the p-val is an imperative language, you can't apply those techniques that are developed for. So, I mean, if you could just mention also the name of the function. You said there is a functional probabilistic programming language.
Certainly. I think there are definitely some.
What are those?
Like there's Anglican, I think, is one. I believe.
How do you spell it? Anglican.
Anglican, like the church. Yes.
Oh, okay. Interesting.
There's definitely other ones. I think. I should really know more of these language. There's another one called. I think there's another one called church actually. Sure. I think Anglican is a pun of church, I believe, or one is a pun of the other. These are kind of probabilistic programming languages built kind of on a Lisp-like or like a common Lisp-like base.
Okay.
There are also languages that are functional for writing differential private queries. One that I'm aware of and have worked on in the past is a language called Fuzz by Jason Reed and Benjamin Pierce. This is a probabilistic language that's based on kind of a lambda calculus. There's many other ones, I think. I can try to give a more thorough explanation later. But I will say that, yeah, go ahead.
Any of these like proof assistants? Are these languages you mentioned? Would they?
It depends on what you mean, right? So I kind of view a proof assistant as a tool for proving mathematical facts about many different things, right? Probabilistic or not. So you could certainly use a proof assistant to prove something about your probabilistic program, or maybe more specifically, you could use a proof assistant to prove something about the semantics of your probabilistic programming language, to prove things about your language. But in that, I think in that view, like whether or not you're studying a probabilistic programming language is not really very important, right? Like it's like proving something about a quantum language would be almost the same, because you formalize in some general logic and you prove mathematically about what this program is doing. But whether you're studying probabilistic or not is not maybe the most important thing.
Right. Yeah. Thank you.
Yeah. But I think one thing that we'll kind of touch on as we go through is that I am presenting things in first order, or kind of wild language first, because I do believe it is much simpler in this setting. I think I'm a big fan of functional programming languages, and I think I got my start in PL kind of learning about Haskell. I really like functional programming languages, and I'm a huge fan. I do think for verifying probabilistic programs, there are some benefits or simplifications you can make for imperative languages that or at least maybe you could say a bit more positively, that the techniques for verifying properties of probabilistic functional programs are much less developed than the techniques for verifying probabilistic imperative programs. I mean, you can use type systems. There are some very interesting type systems. But I think more is known, let's say, about how to verify probabilistic imperative programs currently. I won't say that's a fundamental limitation or anything. Just today, more is known about that, and it's simpler to present. So I hope to talk a little bit about functional languages in the last lecture, but will depend on the time. And again, it's a big area, and there's a lot that could be said about that.